Hello and welcome back. We are starting on I guess this is technically our seventh topic. No, sixth topic, but week 7 of classes since this is happening after reading week this term. And we are going to be talking about searching and sorting. This set of videos is going to have a lot of videos just because there are so many different aspects and it can be really overwhelming to talk about lots of different algorithms all at once. So take each of these videos as they come in sort of smaller chunks so that you can digest the information a little bit easier. All right, so this video specifically is going to be talking about writing code that implements a linear search as well as code that implements a binary search. Now, I did write array here to be searching through an array for these, but it could also be an array list, which is technically an array under the Java hood. So it's really any contiguous memory data structure that we can implement these types of searches on. Okay, so let's talk about searching for a second. How would you search through a phone book? In person, I would really wait for you to, tell me, or perhaps I'd even bring a phone book in. So the first option is you could start on page 1 with the first entry and look at the name. And if it's correct, you can stop. Otherwise, you'll go to the next entry. And you can just keep doing this entry by entry, page by page until you find what you're looking for. But if you're looking for the last name Wondersmith, with a W, of course, it makes no sense to start on page 1, entry 1. You already know it definitely won't be there. You may not be able to pick exactly where it's going to be, but you know it's not going to be on that first page. There's a good chance it's somewhere in the second half of your phone book, right? So since we know it's going to be sorted by last name, that just doesn't make any sense. What if the phone book wasn't sorted though, right? We knew a phone book is sorted, but what if for some reason we had this list and it wasn't sorted? Then we would probably have to go entry by entry until we found what we were looking for, or, explode from going through a bazillion entries and maybe never finding it. So this is two different ways of looking for data in data sets, right? Some ordered data sets, some not ordered data sets. And when we're searching, we're looking through an array or an array list or some kind of list for a particular item. We're looking for a target value or a key value within a list of elements, within a list of values. So there are two different ways to do this. We have the linear search, which is starting on page 1, entry 1, and going element by element looking, which we've done many times. And then there's also, pardon me, there's also the binary search, which is kind of like looking through a sorted phone book, kind of. Because it has to be a little bit more deterministic since it's an algorithm, it's not quite the same, but it is very, very similar, as we will soon see. We're going to start with the one that we're all probably really comfortable with, even if we didn't know that it was called a linear search, because this is when we just search from the beginning to the end of a list for a specific piece of information. We look at every single item, one after another, until we either find the item or we do not, right? This is exactly what happens in a dot contains or a dot index of. We're going to be doing a element by element array list search. We don't need these elements to be sorted because it doesn't make a difference. We are going one by one in a for loop or while loop or whatever it is until we either find it or we don't. We're going to take a look at this in some pictures. And then we're going to put some code together, linear search.java code, and we're going to look at it in Python tutor as well, just to sort of see what it looks like. So let's start by looking at this in pictures. So here we have some array. The data is all over the place. There's 8 elements, index 0 to 7, and we're looking for the value 9. Now, again, this data is totally unsorted, so we have no way of really knowing where in here it's going to be. So we just start at element 0, and we say, are these the same? Target and array at 0. They're not. Let's go to the next one. And the next one, they're not the same. They're not the same. They're not the same. Oh, we found it. Target is equal to the array at 4. So we did indeed find it at index 4. Right? Very, very straightforward, one after another. Okay, let's go and code this up. Oh, my meeting controls are once again in my way. Public class linear search. Linear search.java. Let's throw that on my desktop, as I always do. And let's make that same array. What was in it? 3, 5, 2, 6, 9, 11. 3, 5, 6, 2, 9, 11, minus 9 and 4, minus 9 and 4. And let's just make sure that this actually, like that I did this properly, because I never know how to hard code an array. I always forget. Let's just take a quick look here and make sure that this compiles. Okay, so that did compile, and the first element will be 3. Yay, okay, I did it properly. Good job, me. Okay, we're also going to have a target, and we're looking for the target being 9. What does this code actually look like? Well, public static will return the index of the element linear. And we're going to take in the array, and we take in the target value. This returns the index of the target in array, or -1 if it does not exist. Okay, so we've written this code before. This should be super, super straightforward for us at this point in time. We're going to make some kind of element to return, which will be our index that we're going to return. Oops, that should be like that. And we should have an int position being 0. And now we can run our while loop. I'm just going to move this out of the way so that this hopefully can come up a little higher. We're going to run our while loop so that we go while our position is less than our array.length and our index is still less than 0. Both of those are true to begin. Oh, brackets are hard for me today. We're going to do our comparison. If our array at the given position is indeed equal to our target, then we found it. Index is equal to position. Otherwise, we can just increase our position. So this is going to keep going. Position's going to keep increasing until we basically fall off the array in the case where the index stays -1. And then we'll end up returning -1. Or at another point in time, if the array position is equal to the target value, our index will change from -1 to some positive value. And then this part of our for loop or while loop, pardon me, will now evaluate to false because index will be greater than 0, well, greater than or equal to 0. And so then we will break out again and return our index again. So let's go ahead and run that code. Found index is going to be equal to linear, pass in our array and our target, and let's just print out the found index all on its own. So in order to test this, we have to test for a number that exists in the array and a number that doesn't exist to make sure that both parts of this code work properly. So this did work. We did find 9 at spot 4, 0, 1, 2, 3, 4. Bah! So that worked. And now let's look for like -10, which we know isn't in there. And it should come back as -1, which it did. Fantastic. Okay, so now the other thing that I suggested that you do here is I had suggested that you go ahead and go to pythontutor.com, which I haven't used yet in class here, but we're going to take a look at it right now. There is a Java version, pythontutor.com/Java. We're going to go ahead and we're going to get rid of the code in there. I'm going to pick up my code from over here, and I'm going to plop it over here. So this is all the code that I just wrote over in Sublime. I'm just pulling it into this visualizer so that we can actually see what's happening. And this will look exactly like the pictures that I drew before, but it's still really nice to see it run. So we start off on the main line 3 here, where we're going to make an array. When I push next, we can see the array gets created. It's a list of object or an object of elements here. We can make our target 9. We can see that that's over here. It's not an object. There's no arrow. Pardon me. Then we can go and we try to run found index equals linear array target. It brings us into this method. So we can see we're no longer in the global frame up here. We're now inside the linear local method frame where we have an array still pointing to the same one thanks to our beautiful shallow copies. Target 9 and our index starts off as -0. Our position equals 0 starts off as 0. So now we can say, well, our position is less than our array.length. Well, our position is 0 and our array.length is 8. So that's true. And our index is less than 0. It is -1. That's true. So while true and true, we're going to go into this while loop. And we can see that we're going to do comparisons between array at the given position, and the target. So our array at the given position is going to be 3, just like before. Those won't be equal, so we skip it, and position plus position becomes 1. And this just keeps happening over and over again until we hit, hopefully, one of the two conditions to be true, which we know right now it will become true. What we can also see happening here is that every single time we hit the bottom of our while loop, we actually do come right back up to the top of our while loop, and this line runs again. Every single time our while loop runs, this line runs because we're checking that condition and making sure it is still true. So now we're going to go back into our loop here and check this if statement. We're going to check if the array at position, our position right now is 4, our array at position 4 is 9. We're going to check if 9 equals our target 9, which it is. So hopefully now our code is actually going to step in here and run line 15. What just happened? Oh, it did do that. It did do that. Okay, sorry. Let me go back for a second to, I don't know why it's showing me this weirdness. Here we go. I want to make sure that I can actually see this run. And for some reason it didn't. Position at 4. Index changed, but for some reason it's not stepping into that if statement. But we can actually see position 4. We go to line 14. We're about to execute it. Once we execute it, position does become 5 because we come all the way down here. This must be a bug in their code because the index did change, but we didn't actually step onto line 15. We should have. We should have stepped onto line 15. Oh, there we go. Weird. I don't know what I did. Hold on. I don't know what I did, and this is going to be problematic for me. So let's just do this again, because I want this to be set up properly. And I don't know what all those little breakpoint lines were, but I don't want those. Let me just jump back in to position being 4. If the position is equal to the target. Oh, there we go. Now I'm stepping into line 15. We can see that those were equal. Index is equal to position. So now our index will change to 4, which it did. Position plus plus, sure, it'll go up to 5. It doesn't make a difference though, because then when we come back up to the top of our loop, our position may still be less than our array.length, so that's still true, but our index is no longer less than 0. This is false, true, and false. We'll evaluate to false, and our for loop will break out. We'll come down, and we will return our index back up, and then we will run our final line here, line 6, where we print out the found index. So that's actually what our code is doing. We saw it in pictures, we saw it in code, we saw it in this animation. That is how the linear search runs. It's not super tricky code by any means. Just gonna make sure I save this before we move on. But it's nice to be able to see it in a variety of ways. So that's linear. Awesome. Let's look at the binary search here. Now, a binary search is exactly what it sounds like. It's binary, so it's like splitting our list in half, like we're cutting our problem space in half. Now, there are some requirements in order to do this. It's way faster than a linear search, and we'll talk about why soon, but it does require that the list is in sorted order, and it does require us to be able to have random access to the list. And what that actually means is being able to say like array, square bracket, and then any position, and be able to just access it without going through every single one. And we will see in a few weeks that there are some lists that don't have random access. All we've seen thus far is lists with random access, arrays and array lists. But again, in a couple of weeks, we will see types of lists without random access, which makes binary search not possible on those data structures. But for our current level of knowledge, we always have fast random access, but we have to make sure that our list is sorted as well, of course. So first, we're going to take a look at this in pictures, then we're going to have code, and then I'll show it in Python Tutor again, maybe. I might just have you do the Python Tutor bit at home, because the pictures for this one are going to be a lot more informative than Python Tutor. So let's look at the exact same array, except now it is in sorted order. So I've reordered it so that we're going from like the most negative number to the most positive number, still looking for the target value of 9. So what ends up actually happening is we're going to split this list right down the middle like this. And then in this case, there is no middle element. So we sort of just get to pick what our element to look at is. So I end up picking the last element on the right side, on the left side. And then we do a comparison here. And we say, is target and array at this position bigger, less than, or equal? So we have to ask 3 questions now. We're not just asking, are they equal to each other? We want to know in which direction we need to go. And since 4 is less than 9, we know that if 9 exists, it's going to be to the right of 4 because it's bigger than 4. 9 is bigger than 4. So now we actually are going to be cutting out all the elements 0, 1 in spots 0, 1, 2, 3, because we know for sure it won't be there because 9 is bigger than 4. So we have to be on the right side. So now we only have to look at the right side, and we can do this process again. We can cut our array in half. We've eliminated those first 4 elements. We've cut the remainder in half. We're going to look at the 6, and we're going to say, well, is this our target? Is our target bigger? Is our target smaller? What is our target? Okay, it's bigger. We need to keep moving to the right. So we do. We cut the remainder in half again, and we grab the element on the left. Is it less than, equal, or greater? In this scenario, it is equal. We found it, and we can stop. So rather than going through every single element, this taking 7 iterations for this array, this only took 1, 2, 3 iterations for this array. So there is a lot more to track when it comes to a binary search versus a linear search. We already saw the code for a linear search. All we had to track was our index, our target, and our array, right? And like a position, I guess, of course. But with a binary search, we have to keep track of more because rather than just searching through our whole array, we're always searching through sub-arrays within the array. We're basically like cutting little pieces of our array and throwing them out as we go. In the linear search, our low index is always 0, and our high index is always array.length minus 1. Those are always our endpoints. But in a binary search, those endpoints shift depending on what we're looking at, what part of the code we need to look at. In our binary search, in our linear search, pardon me, when we reach the end of the array, it was obvious to us if we reached the end and hadn't found it, that the element didn't exist. For a binary search, how can we check for that? We're going to watch for high being less than low, which makes no sense. How could our high index be less than the low index? Well, it can't, right? That doesn't make sense. So if that happens, if our 2 borders have shifted enough times that what ends up happening is high ends up being like a bigger number than low, what ends up happening is those cross, and when those borders cross, that means we never found the number. Okay, so let's look at that code now. Public class binary search .java. I'm just gonna grab this really quickly. It's gonna be different, of course, because these have to be in sorted order now. So it's like -9 2 3 4 5 6 9 11. There we go. Okay, so now that's in the sorted order that we just saw in that other image. And now instead of calling binary, instead of calling linear, we're going to call binary. Public static int binary, and it will take in the same information, target. And now we're going to go ahead and track all the same variables that we just talked about. So we need to have a low index, which we know when it starts is 0. Because when we start, we look at our whole array. And we need to track our high index, which when we start is array.length minus 1. That's the very last element in our array. We also need to figure out where to cut that array in half. So we have our 2 endpoints, and we can add them together and cut it in half. So we can say high plus low divided by 2. We can cast this. We can, pardon me, do lots of things. We can do a math.floor so that we're always cutting it. Like it helps us cut it when there's an odd number of elements. Like if there's 5 elements, how do you want to cut it? Well, I'm deciding I'm going to cut math.floor, which means 2.5 becomes 2, 3.5 would become 3, etc. Right? If we have 7 elements, 7 divided by 2 will cut us in half, will become 3.5. Math.floor will make it 3. Things like that. Okay. Those are words. That's okay. Those are words. All right. So we have our int low, our int high, our int mid, and then we also needed to keep track of our target and our array, which we already have. The only other thing that we should probably actually keep track of is that found index, right? We have to make sure that we actually, at some point, return the found index if we find it. Okay, just do this. Now, we already know what our not found condition is. We said it is when high ends up being smaller than low. So while low is less than high, we can go looking for our value. While low is less than high and our found index is less than 0. We have to include that again just to make sure that if we do find it, we don't need to keep looking, we can just stop. Now, if our array is empty, low will be 0, high will be 0, 0 divided by 2 will be 0, our mid will be 0, 0 is not less than 0, we don't go into this, it will return out. So even in the base case of like an empty array, we can still see how this is going to work. So that works out okay for us. So now that we have our low, our high, and our mid, we have to figure out how exactly we're going to be checking for the target. And if you remember in the picture graphic animation that I showed, I basically took mid and I compared it to target. And that's what I did every single time. So let's just flip back and look at it again really quickly. In this, actually I didn't. I did mid minus 1. Do I like that or do I hate that? I actually think I kind of hate that. I'm going to program it maybe a little bit differently, but that's okay. It's just an implementation choice. We divide this in half, so we have 8 elements, and when I divide 8 by 2, I end up with 4, and so then like the value 4. So then I'm going to actually end up looking at 0, 1, 2, 3, 4, and so I'm going to end up looking at the 5th element here, the 5th element here because that's what's at index 4 when I do math.floor. My initial example showed me doing the midpoint minus 1 as opposed to just whatever the midpoint happened to land me on. That's the only difference. So that when I was running through it here, this was mid minus 1, but now we're going to just treat the if statement to not check mid minus 1. It's just going to check mid, and we're going to keep going with that information. If mid and target are equal to each other, we found our target. We found it. That's awesome. In fact, we found it at mid. So we're done. That's great. But there are 2 other cases that we have to consider. If they're not equal to each other, mid could be smaller than our target. And if that's the case, let's flip back. If mid is smaller than our target, we need to move our low and our high to become low and high, right? We're shifting over the bounds of our array. Rather than low and high being here, low has to move here and high will stay here. So high doesn't change, but low does. And we already checked mid in theory. So this actually becomes mid plus 1. So if we need to move to the right side of our array, our low becomes our middle point. Now, the final case here is if it's not equal and it's not less than, it must be greater than. And if our midpoint is greater than our target, we need to start looking on the left, which means our low doesn't change, our high has to change. And that's it. That's all that happens. So let's walk through this example just super quickly with this array here, 1, 2, 3, 4, and let's go looking for the value 0. Just so that we can see, actually, let's first look for the value 1, and then we'll look for the value 0. So if we're looking for the value 1, low will start off as 0, high starts off as array length minus 1. So high starts off as 3, 0, 1, 2, 3. And then our not found index, or our found index, pardon me, is minus 1. Now, our mid will be 3 divide, we better make this high just be the top of it, so array.length exclusive, so that this becomes 4 divided by 2, which is going to be 2. So our midpoint here is going to be 2. So 0, 1, 2. So we're going to check this value against our target. 3 and 1 are not equal to each other, so we do not go into the if statement. Next, we look here. Is 3 less than 1? No, 3 is not less than 1, so we go into our else, and so our high is going to change. Our high becomes mid minus 1. Remember that our mid was 2, so now our mid is going to be 1, which it shouldn't be. It should just be our high should now just be mid, and this just matters because I changed that minus 1 up here. This is why we walk through it. High equals mid. So our mid was 2, 0, 1, 2. So now That's basically all that's left. We have low at 0 and we have high at position like 3, which doesn't exist, right? 0, 1, 2, because there's 3 elements. Okay, we come back up to the top. We can see that low here is going to be, I should like be writing down each of these and like updating them appropriately. Low is still 0, high is now 3, and mid is still technically 2, and found index is still technically -1. So now low is still less than high, and found index is still less than 0. So now we're going to compare our array mid to our target. Well, our mid didn't change. It probably should have. So check that out. We now realize that there's another error in here. Our mid has to update along with our low and our high. Every single time that this runs, our mid needs to be high plus low divided by 2, and all of this needs to be floored. Math.floor. Floor. Perfect. So now when we do this, we end up with 3. Is it high plus low? High minus low? That'd be high minus low. Can we tell that my math skills are like incredible? High minus low. So we take 3 minus 0. 3 minus 0, and we get 0. We divide that by 2, we get 1.5. We do math.floor, and we end up with a midpoint of 1. So now we can compare our array at spot 1 with our target 0, 1. They are not equal to each other. Is our array at midpoint less than the target? No, 2 is greater. So we go into our else, and our high moves again. Our high moves to our midpoint, which is at 0, 1. There we go. Now we can do our mid calculation again. So our high has now been moved to here, and our low has not changed. So 1 minus 0 divided by 2 is going to be 0.5. And when we do 0.5, the floor of it, we get 0. So now our midpoint is, in theory, 0. So now we say if our array midpoint is equal to target, our array at 0, it is equal to target. So found index equals mid. We come back out. This changes, but it doesn't matter because we come right back up to the top, and now our found index is 1 or is 0, and 0 is no longer less than 0. So we break out and our found index works. Let's actually run this code and make sure that it works as we expect it to. And let's use the array we were just talking about. Since we walked through that, we can make sure that it works as we expect. We expect our array to return nothing because apparently I did something wrong here. And target. We expect our array to return 1. Oh, it's upset that math.floor requires this to be an int. I would have assumed it would figure that out, but it did not. That's okay. There we go. Okay, and now we can run this Java binary search, and it returns 0. So that actually did work. That's amazing. And if we put this array, oh, this sucks. If we put this array back to what it was, which was like -9, 2, 3, 2, 3, 4, 5. What was it? 2, 3, 4, 5, 6, 9, 11. 6, 9, 11. And we go looking for 9. We should find it in position 0, 1, 2, 3, 4, 5, 6. We should find it in position 6. Let's make sure that that's actually what happens. Let me just clear this so we can see this a little bit easier. Uh-oh. It didn't work. Oh no. So let's go back and debug our code to see what's going on. So when we come in here to actually figure out what's going on, one of the best things that we can do to test this is to go ahead and print out each of our values. We can print out our low value, we can print out our mid value, and we can print out our high values so that we can make sure that these are exactly what we're expecting them to be. I think I know what's going on here, but we're gonna debug this as if I don't know. Okay. Check that out. It is 328 always and forever. It never changes from 328. Let me just do a Control C here to stop it, and let's see if that's what it started at. Oh, it's even too long for me to find that. So the very first time it runs, it wouldn't be 328 because the first time it runs, we know that low was 0. So we know that we are eventually reaching 3 and 2 and a midpoint 3 with a midpoint of 2 and a high of 8. Well, that doesn't make any sense. How could this be our midpoint, right? So now we can actually see Oh, Lauren, it absolutely was supposed to be plus. You're just not that smart. So this becomes plus, and this becomes plus. And now when we run this code, we actually will end up with appropriate midpoints. One of the easiest little mistakes that I could have possibly made. And of course, now we can see we do get the correct output, which is a found index of 6. Silly me. Okay, we now know that our code does indeed work. We should make sure that it also works for the case that we originally tried, just because we've changed our code. So we should make sure that this doesn't break our code, which of course it does not. And then we can also do a final test here for a number that doesn't exist and make sure that we do get -1, because that's a really important test to do as well. And it totally works, which is awesome. So now we have our binary code in there properly, where we're correctly setting our low, our high, and our midpoint. We're correctly assessing what side of the midpoint our target is going to be on. And then we are correctly recalculating our midpoint based on the adjusted ranges. So all of the pieces for our binary search are now in here. Yay! Binary search can be a little bit trickier to sort of follow, so it's always really nice to draw it out to get a better feel for it. Okay, so let's talk about the time complexities now between these. Now, it's pretty obvious when we just talked about iterations with our linear array, we had to go through 6 iterations to find the 9 in the sorted linear array, right? So when we look at our array, right, how do I zoom in? Right here, and we look for our target, and our target goes back to being 9, we'll have to look and compare this number, this number, this number, this number, this number, this number, and then this number, and then we find it linearly, right? Because we're going one after another. When we did it binary search, first we found this side, then we found this side, and then we found it right here. It only took 3 checks as opposed to 7 checks. So it's pretty obvious when we just look at it like that. But there are actual ways that we can formulate this idea of how long it takes to run something in a little bit more of a formal and professional like notation. Okay, so linear search. What does linear search take? Well, it takes linear time. What that means is if we have 10 elements and we're looking for an element, it's entirely possible to find that element right at the end in the 10th spot, and it takes 10 time steps. It's possible we find it in the first spot, which would be great, but we can't always guarantee that. It's just as likely to find it in the first spot as it is to find it in the last spot. So in the very worst case, if we have n elements, it's going to take up to n iterations of that loop, n comparisons to see if we can find it. So linear time means that as n grows, the number of steps grows at the exact same rate. 10 elements, up to possibly 10 steps. 20 elements, up to possibly 20 steps. 100 elements, up to possibly 100 steps. They grow linearly. They grow together at the exact same rate. So it will do a number of operations that is linear in comparison with the size of the input array. And this is all worst case, right? Of course, best case is we find it on the first try and it only took 1 try and we only have to do 1 operation. But as computer scientists, we have to think about it a little bit differently. We can't think about the best case. It's nice to know that that's an option, but we have to know what the worst possible case is. We have to know, like, I don't know, computer scientists, I guess, are super anxious. That's not really why, but it's probably also true. We have to make sure that we know what the worst case is so that we can appropriately plan for how long something maximum could take us. What's the maximum amount of computing power we need? What's the maximum amount of time that we need to produce results? People don't really care about what the fastest is. If I need to get test results back, sure, it's great to know that the fastest is 5 minutes, but like that doesn't really mean anything to me. I need to be able to plan and know what the longest is. To know, okay, I will for sure get my exam results back within 2 weeks, 2 weeks at the latest. That's the information that I need to know so that I can appropriately plan my next steps for my degree. Sure, in theory, I could get it back in 5 minutes, but that's not really that helpful because like if I don't, then what? So what's really important to us is to know what the longest time is. So this worst case would take n operations for an element of size n, that linear growth. Okay. So now binary search. This is different because we don't have to look at every single element. Our problem space shrunk by half every single time. And it shrunk to half of the current size. So first in an array of size 12, it shrinks to 6 and then to 3 and then to 1. So it's not like it shrunk by 6 each time, right? It shrunk by 6 and then 3 and then down to 1 because it took whatever the current rate, like high and low range number of elements, it took that and cut that in half. If we have 16 elements, it shrinks from 16 to 8 to 4 to 2 to 1 to 0, right? Every single time it cuts it in half like that. We're throwing out half that array each time that we iterate. So look here, we can see list sizes of 10, 20, 1,000, a million, and a billion? Trillion? Billion. A billion. I'm good at things. We can see how many possible iterations it would take to do a linear search on a million elements. We have how many people in Manitoba? I think we have like 1 million people in Manitoba. So if you have a Manitoba phone book and you're looking for somebody with the last name that starts with a Z and we're doing a linear search, it could take up to 1 million checks to find that answer. But a binary search, it actually takes on average only 20 checks. That's it. Every single time we cut that problem space in half. There used to be this like old weird trick where it's like if you took a piece of paper and you folded it in half, you could only fold it in half. It's like 6 times or 7 times before it literally becomes impossible to fold again. Doesn't matter what size of paper you start with. Try it. It's insane. And I'm not talking about like just tiny little like corner folds. You have to fold it in half each time because that's what we're talking about. It's like that binary thing. You can't fold it in half more than 6 or 7 times before it becomes like too thick to be able to fold it. I wish I remembered the exact number, but it's a crazy thing and it's totally true. And that's the same phenomenon that we're seeing here is that on average, because we're cutting our size of our problem in half each time, it only takes 20 iterations for 1 million elements. If we look at a smaller number of iterations for like a list size of 10, we know that we'll have to do a check for all 10 elements, then 5 of the elements, then 3 of, so all 10 elements, 5 of the elements, 3 of the elements, 1 element, we found it or didn't find it. So that's 4. For 20, we go from 20, so the iteration on 20, an iteration on 10, an iteration on 5, an iteration on 2, and then an iteration on 1 takes 5. We can see how just doubling the size only added 1 binary iteration, even though it literally added double linear iteration. So while we can say that the linear iteration, like the linear search, is growing linearly with the size of the number of iterations is growing with the size of the array, we can see that that is not the case with binary. In fact, it's not just cutting it in half, it's not cutting it into quarters, it's growing it's logarithmically. It's growing by log n. So it grows a lot slower. And we'll talk more about that sort of mathematical notation later. So when do you actually need to use a binary search? Well, you need to have sorted data, right? We saw that it has to be sorted. It doesn't work if it's not sorted because we can't do comparisons if it's not sorted. You can keep your data sorted as you build out your array, or if you somehow get an input array and it's all over the place, you could sort it. Or if you get a sorted list by default, then you can use a binary search too, right? So there's all these options. If we have unsorted data, we could do that linear search, or we could do a binary search and then sort it. Right? Sort it and then do a binary search. Words are hard. So we have lots of options here. However, keeping a list in a sorted order or sorting the list first and then doing a binary search can actually sometimes take longer than just sitting there and doing the linear search in the first place, which is super interesting because it kind of is like, what's the point then of doing a binary search and like knowing about it if sorting our data in order to use a binary search would take longer than just going entry by entry in the first place? Well, we can use a binary search if our data happens to already be sorted. That's always an option. Another really great use case for a binary search is if you plan to do a lot of searching and your list of data doesn't change that often. So keeping it sorted is really easy. So like think about genetic encoding for a second and think about like sequencing a genome and then looking for genes in it. Once the genome is sequenced, all we're doing is searching. So yes, that first initial sequencing might take a really long time. So overnight maybe, right? Once we're sorted, though, the searches quick and easy and fast because we are sorted. So sort once, search many times. It might make sense to do a sort and then a binary search. If we know we're going to be doing lots of searches, linear searches constantly might actually take more time in that scenario than just running a very long time sort, like just it taking forever, but whatever, and then being able to search with no problem following that. What we can see happening here is that planning the requirements of our problem space is incredibly important. We can't just always use linear search. We can't just always use binary search, and we certainly can't just assume that since binary search is faster than linear search, it is also true to sort and then search everything as a way to be faster. None of that is necessarily true, and it's all very dependent on the problem space, and we can really see that happening here. So we're going to talk about the sorting algorithms that we could use and the speeds of them and how that affects this whole process in my next few videos, where I'm going to talk about each of the different ones in different videos and program them in different videos. But for now, we're just going to do a pause and practice of these different types of searches. So here is a sorted array. How many comparisons would we need to do with a target value 9 in this array for a linear search? So how many times are we actually going to do our comparisons for a linear search? Now, linear search does not assume any form of order. So it will go through this whole array based off of our linear search that we programmed, looking for 9, and it keeps going. Now, as for a binary search, and of course, there's ways to modify that linear search, given that this is sorted, to stop once it's no longer possible that it would be in the array, right? But I'm talking about the most naive linear search, the one that you're going to go look up that I just uploaded, linear search.java. How many times will that loop run looking for the target 9 in this array? And then ask yourself, how many times does that loop run when we're looking for the target 9? But we're now implementing a binary search. So looking at my binary search Java file. So consider those two different cases, see the time difference in terms of like number of iterations, get comfortable with those two different types of searches, and then meet me in the next video where we're going to talk about the different ways to sort our array data.